We're working through 2.6 Related Rates Worksheet 1 on the back page here, number 4. A tank of water in the shape of a cone is leaking water at a constant rate of 2 cubic feet per hour. The base radius of the tank is 5 feet and the height of the tank is 14 feet. So we're given dimensions of our cone here. 5 feet is the radius, so I have a diagram here showing the radius of the cone here, and the height dimensions of the height here will be 14 feet. Part A, at what rate is the depth of water changing? So we're trying to find, we know depth is in relation to h, height, and we're trying to find the rate of the height, so we're trying to evaluate dh dt when the height or the depth of water is 6 feet. So we're given some information. We're trying to find dh dt at the moment that height is 6 feet. We're also told that water is leaking at a rate of 2 cubic feet per hour. We know that cubic feet is a reference to volume per hour, so we know that's dV dt. So dV dt is -2, and the reason why it's -2 because water is leaking out of the cone, so we know the rate of change of the volume is going to be decreasing, so decreasing means negative. So let's see what else we know. We know there's going to be a similar right triangle here, a similar triangle problem. So dimension of the cone of the tank is radius 5, height 14. The water level at any moment in time will be radius r and height h, since that's unknown at this moment. With this information, we can set up proportions here. So we can say small radius is to big radius as small height is to big height. So r over 5 is equal to h over 14. We're working with the volume equation of the cone, which is pi over 3 pi r squared h, and we know that we're trying to rewrite our equation in terms of just volume and height. The reason why is because we want to find, when we get down to the equation that has just h in it, then we can find dv dt and dh dt without having to deal with dr dt, which is not information that we need or have. So we want to replace r. So to replace r, we have to find an equation that's equivalent to what radius is. So that's where the proportions come in. So if I solve for r, cross product here, so 14r is equal to 5h. Solve for r, that just means divide by 14. So 5h over 14 is equal to r. Replace this in for the r, so we get pi over 3. Sorry, this should not be a pi here. So it's just pi over 3 r squared h. So the r gets replaced with 5h over 14 quantity squared times h, and 5h becomes 25h squared over 196, and then the h squared times h is h cubed. And once we make the substitution here, we still want to continue cleaning up. I think some students want to jump directly into finding the derivative, the dv dt. You could, but it's going to be a little messy having to go through product and chain rule. So why not just clean this all the way up, and then we can just resort to simply using power rule. So 25 over 196 is the result of 5 squared over 14 squared. H squared times h becomes h cubed. And if I combine the coefficients together, I get 25 pi over 588. The 588 is coming from 3 times 196. So now the equation is going to be a lot easier for us to find the derivative now that we have coefficient h cubed and v. So v becomes dv dt. 25 pi over 588 is just the coefficient, so it's just going to stay out in front. H cubed, we can just resort to a power rule. So h cubed becomes 3h squared, and then attach dh dt. Now we can deal with h equals 6 and dv dt equals -2. Again, we don't want to plug the 6 in too soon, because if we plug in too soon, we lose the ability to find dh dt, which is what we're trying to find, which we're trying to solve. All right, so now dv dt gets replaced with -2. H becomes 6. So 3 times 25, I made that 75. So 75 times 36 divided by 588. All this works out in our calculator to be -98 over 225 pi. and we're trying to find dHdt, so dHdt is going to be feet per hour. Okay. And then for part B, it says at what rate is the radius of the top of the water in the tank changing? So actually are trying to find information with drdt. So rather than having to go back to the equation and trying to get everything in terms of r and then find drdt, we have a bit of a shortcut here because we have this information that will allow us to find drdt. So if we do cross product here, we get 14r is equal to 5h. And from here, if I find the derivative with respect to time, 14r becomes 14 drdt, 5h becomes 5 dHdt. We just found what dHdt it was, so if I plug this in for dHdt, then I can solve for drdt. So divide both sides by 14, replace dHdt with negative 98 over 225 pi, and if I clean all this up, I get negative 7 over 45 pi. Again, same unit as dHdt, which is feet per hour. Number 5, Jet A travels due east from San Francisco towards St. Louis. So this is the path of Jet A towards St. Louis. Jet B is starting in New Orleans and has to travel due north to get to St. Louis. So we see the path of the triangle, and the distance between the two triangles at any time is going to create a right triangle, and that's the equation that we're working with. We're working with Pythagorean theorem and right triangle here. All right, we know that Jet A is traveling towards St. Louis at 500 miles per hour. However, if you think about what's happening to x, dx dt represents the speed of the velocity of Jet A. But as Jet A travels towards St. Louis, we see that the length of this distance between Jet A and St. Louis is going to be decreasing, so we want the rate of change between Jet A and St. Louis to be negative, so negative 500 miles per hour. Jet B is traveling to north, and the distance between Jet B and St. Louis is also decreasing over time, so we want dy dt to also be negative 600 miles per hour. All right, we know we're working with Pythagorean theorem, so I'm going to set up the equation here. X squared plus y squared equals z squared. If I find the derivative with respect to time, x squared becomes 2x dx dt, y squared becomes 2y dy dt, and z squared becomes 2z dc dt. Now let's see what we have here. We have dx dt, we have dy dt. We're trying to find the rate of change of the distance between the two jets. So we're trying to find dz dt. That's what we're after here. So to find dz dt, we need to fill out more information in terms of the variables that's missing. So let's see. We know Jet A is 100 miles from St. Louis. We know the rate of change. We know that the moment in time we're talking about the distance between two jets is 300 miles apart, so that's going to be z. So if we know x and z, we can use Pythagorean theorem to find y. So x squared plus y squared equals z squared. If we subtract the z squared and then solve for y, we're going to get 282.843. So we have x, y, and z. We have dx dt, dy dt. So we have 5 out of the 6 variables accounted for. So we can then solve for the 6th variable here. So replace each of the variables from the information that's given here that we found, and then we just have to solve for dz dt. So the rate of change makes sense that the rate of change is going to be decreasing at a rate of negative 732 miles per hour. All right, number 6 here. The trough shown in the figure below is 5 feet long, and its vertical cross sections are inverted isosceles right triangles. Okay, 2 feet, 5 feet, and 3 feet. Water is being siphoned out of the trough at a rate of 2 cubic feet per minute. At time t, let h be the depth and v be the volume. Find the volume of the water in the trough when it is full. I'm going to the next page where I have the solutions worked out here. So if we think about the volume of this trough here, there's going to be a length, width, and height component. So let's think about the area of this triangle, and we can multiply by 5 to get that third dimension. So volume is going to be 1/2 base times height, so 1/2 2 times 3 times 5. And so this is going to be the formula for the volume of the trough here. So part A says find the volume of the water trough when it is full. So we just need to find the volume of the trough. So 1/2 times 2 times 3 times 5, so 15 units cubed, okay, or cubic feet. Part B, what is the rate of change of H the instant when trough is 1/4 full by volume? So we need to first set up proportions here. We're not going to deal with the right triangles. We're just going to deal with two similar triangles here. So we have the base of the trough here, which is going to be 2. We know the height is 3. And then the water level is going to have a certain height and a certain base. So if I set up proportions here, I can say B over 2 is equal to H over 3. So small base is to big base, and small height is to big height. And the idea here is we're trying to find dH dt. So if we want to find dH dt, and we're working with the equation of 1/2 b times h times 5, or 5/2 bh, we want to replace b in terms of h so that we can just have h in the equation, which will make it a lot easier to find the derivative, and then therefore allow us to arrive at dH dt. So if we solve for b here, cross product, 3b is equal to 2h. And if I solve for b, b is 2h over 3. Here's our equation. Replace b in terms of h. So b gets replaced with 2h over 3 times 5/2. The 2's cancel out, so I'm left with 5/3 h squared. So this is our updated equation. Volume is equal to 5/3 h squared. All right, so now we're ready to find the derivative here. So v becomes dv dt. 5/3 h squared, the 5/3 stays, we just have to deal with the h squared, so 2h dh dt, which becomes 10/3 h over 10th h over 3 dh dt equals dv dt. So now let's see, we want to find out when the trough is 1/4 full, and when the trough is 1/4 full, we can use that information to find h. Now we know the volume is going to be 15. 1/4 full will be 15 over 4, right? 1/4 full. 1/4 the capacity of the volume of the trough, so 15 over 4. So since volume is 15 over 4, we can use that to help us find the height. We know the height, we know volume is 5/3 h squared, so if I set that equal to 15 over 4, which is the volume of the trough, I can use that to solve for h. So if I divide both sides by 5/3, or in other words, multiply it by 3/5, I'm going to have h equals 3/2. Okay. And if h is equal to 3/2, then I can, we know h squared is equal to 3/2. Sorry. And if h squared is equal to 3/2, then I can replace h squared with 3/2. (10h over 3 here). Let's see, 15, 5, 1/4. Okay, right. So I'm sorry, h is equal to 3/2. So when h is 3/2, we can plug that in for the h here. So 10/3 times 3/2. We know dv dt from part A, which is telling from the original problem, which tells us that water is being siphoned out at a rate of 2 cubic feet per minute. So we know the rate of change of the volume is going to be decreasing at a rate of -2 cubic feet per minute. So -2 replaces dv dt, and then from here we can solve for dH dt, which will allow us to get down to -2/5. So we know dH dt, we know the rate of change of the height of the trough is -2/5 feet per minute. For part C, what is the rate of change of the area of the surface of the water? So if you look at the surface of the water, it is in the form of a rectangle, right? And the width is going to be b, whatever that b is at that moment in time, but the width or the length will always be 5, right? So we know the area of that rectangle of the surface of the water will be 5 times b, And we know B in terms of H is going to be 2/3 H, since we found that from here. So 2/3 H. So then if we clean this up, we have A is equal to 10/3 times H. If we want to find the rate of change of the area of the top of the water level of the water surface, then we can find dA dt. So to find dA dt, we can go through derivatives. So A becomes dA dt. 10/3 H becomes 10/3 dH dt. We know the rate of change of the height at that moment in time is negative 2/5 feet per minute. So 10/3 times negative 2/5 becomes negative 4/3 square feet per minute.